Hey everybody, this is part two of Why Learn About Artificial Intelligence Now. And these introductory lectures really are intended to just give you a broad overview of some of the concepts, get you excited about what the potential is for artificial intelligence and algorithm engineering, and introduce you to the concepts. We'll be covering many of these concepts in a lot of detail in future lectures. So one of the challenges of deep learning, to kind of continue on this topic, is we can basically teach the computer what a specific image is, but we really don't understand what's in the scene, and that's more complex. A project that I've been involved in is animal behavior, and to try to understand if an animal, such as cattle in a feedlot, by using behavior to understand if they're sick, is one of the projects that I've done. And what's interesting about it is, how does a cowboy looking at a cow in a pen understand if it's sick? Well, it looks at its droopy head. If it's slow to the trough, it has all these kind of behavioral things that are really more than just an image. And so that's one of the challenges of deep learning. And then also, when I go off and create models for these things, I try to find a large database. And so the scene, which I'm taking in images, is not a cartoon. And there's all these other challenges. The lighting may change. There may be variance, and in this case, you have a high solar signal in the bottom half of the image, and you may have a partial image of the face if you're doing facial recognition. And in machine learning, some of these issues with variance and scale and orientation and lighting gradients all become challenging and make your model and the amount of data that you need to have really explode. So these are some of the challenges that we see, especially in imaging type applications. And oh, by the way, I've gotten a lot of this background information and really enjoy presentations by Lex Friedman, who's an MIT lecturer on this topic. So you can go to him as well and search on his name on YouTube and find a lot of good lectures on this topic, the challenges of deep learning. So let's talk a little bit about these in detail and maybe how we can overcome these challenges. So this is an example of image variance. So you can see that we have different lighting gradients here, and we're trying to do facial recognition, and we may have some scale challenges, where the face may be of different sizes slightly, and the cat down below has different scale problems, different orientations. This one, unless you're kind of looking at it and know what you're looking at, you may have a difficulty in understanding what that image is just as at the human level. So you see all these different variants. So the challenge is to overcome these things with deep learning, and it takes a lot of data and a large model to be able to do that. And here is another type of challenge, right? So this is one of my favorite images that kind of demonstrates, well, how do you know what humor is in an image, and how would you classify that, right? You've got people smiling, but the real humor is that President Obama's got his foot on the scale and everybody's in on the joke, but this guy's not, right? And you have all these other challenges. You have a mirror in the image, 2 mirrors, 3 mirrors, faces that are all focused on a specific topic. There's some kind of structure or inference that's a part of this to understand really perception that there's humor in this image. So those are really advanced concepts, and how, if at all, then can you teach a computer to be able to learn and make judgments on this. And then finally, another challenge is really AI system a computer needs all of this memory and images to be able to create a solution, where humans really learn from very few examples, right? You think about just walking one day at 10 months old, 11 months old, child raises its hands and stumbles around, and all of a sudden it is walking, and went from crawling to walking very quickly. And machines, in most cases, need thousands or millions of examples to learn effectively in every situation, right? So those are some of the big challenges. What I'd like to turn to now is introducing some of the key concepts that we're going to be learning in the class, touch on them to give you an introduction, help you in your reading, help you in the future videos, and just get the nomenclature terminology down. So key concepts from feature engineering, which we'll talk about in just a second, and then there's this idea of input layers. And so these are the samples. This may be a sample with multiple features, and that's what is called an input layer, also called just your X values. This is an example of a hidden layer, and then we have the output layer, and if we're looking for a dog and cat, that's 2 different classifications, and then your samples are either labeled as a cat or a dog, for example. We'll use a technique called gradient descent. We'll look at the errors and then compute the weights based on this technique called gradient descent. And it's really looking at the loss, an error loss between our target value and what we predicted the value is. And that's going to be real important. And then also the concept of an activation function. An activation function adds nonlinearity so that you can model things that are not linear. If you just thought about a single layer, and we will use really a weight times the input feature x plus b, a bias. If you thought about that, that really is nearly like a multiple linear regression problem. Well, adding this concept of an activation function allows you to model things that are nonlinear. Weights, we've talked a lot about, really deep learning is all about how we adjust the weights to minimize the error in our model. And then the loss function is where we're taking the difference between where predicted value is and our target, our actual value, and using that loss function and then having a method called backpropagation where we look at and we optimize the weights to reduce the error using this technique called gradient descent. So forward propagation basically is you go through the model in the forward direction, and then you backpropagate and recalculate each of the layers' weights based on this technique using the chain rule, and we'll have a whole lecture on how to do that through the layers to calculate the new weight values. So those are some important concepts. We're starting to introduce those. Feature engineering, the way I like to think about feature engineering is how do you represent your samples, the features in your sample data so that it's easy to learn. Here's a simple example. If you have a Cartesian coordinate system that looks like this, separating these two groups may be more difficult than if you had a polar coordinate system that we're using. So it's really about how do you map the problem so that the final information is really easy for the model to work with. In narrow artificial intelligence applications, you do a lot of feature engineering because you're trying to reduce the compute power that's needed. You're also trying to reduce the amount of data that you used. And so the more feature engineering you can implement in today's type of deep learning applications, actually the less resources that you need. And so we'll spend some time talking about feature engineering. The technique I like to use is, well, what if a human does it, what are you thinking about as correlation? How can you tell that a cat is different than a dog if we were to explicitly write that down? And for example, or if you're looking to make a prediction on what team is going to win the next game in the NFL, what factors would be correlated to the features that would be correlated to who would win the next game. So that's the concept of feature engineering. We'll talk a lot about that in the class as well. And then this idea of creating training and test sets, very important. Training stage, you'll have your input samples, your input data, you'll create a model, have a learning system, and then you'll have the output, and you'll compare your prediction versus the ground truth or the gold standard. And iterate over and over again on the training stage, and that may be 70-80% of your data. And then the idea is to reserve a set of data that your model has never seen, and then make a prediction. And so if the accuracy error between your test stage is different than your training stage, then you've overfit your model. And we'll talk a lot about the challenges of identifying overfitting and how to reduce overfitting. And that's an important concept. Training, test data, as well as overfitting of models. So really, the core of how neural networks work is this technique called backpropagation. So you have a forward pass where you input the data, you have existing weights in the neural network, and you make a prediction. Well, the key point of backward propagation or backpropagation is that you measure the error and then you change the neural network. You change the weights and the biases in the nodes of the neurons in the neural network so that you reduce the error, improve the accuracy of the prediction. And so backpropagation is an important concept. Another important concept is this idea of regression versus classification. You can have machine learning systems that will give you a continuous output prediction. And so temperature or weather is a good example of that, where classification is I have a number of outputs, only a discrete number of outputs. In this case, cold or hot. We have two outputs. The binary classification, is it going to be cold or hot tomorrow? And so depending on the type of problem that you have in narrow AI, you will define and build your model differently depending on if it's a regression or classification problems. So there is a biological inspiration for an artificial neural network, and it's this idea of a axon with a nucleus, and you have all these dendrite inputs. And how that's abstracted into the compute world is you have this idea of a cell body, and then you have the features or the X values for a particular sample. So a sample may be one image, and then each feature is a pixel in the image. And then what we're trying to do is integrate and all of the features and adjust the weights based on those input features plus a bias, and then use a nonlinear activation function to create an output and create multiple hidden layers so that we can model the system. And so really the derivation of this neural network is really a biological inspiration from the real world neuron. And so we'll spend a lot of time talking about weights, input features, doing backpropagation, but to introduce you to the concept that this is really biologically inspired. Now, really the ability to create a sophisticated model is a function of the data set you have. How good is your data set, which is this is your input layer, which is a set of features of one piece of data, and then we're going to expose a second sample and then test the model and then adjust the weights in the neural network and then aggregate what is the best set of weights across the entire training data set that you have. So that's the idea, is to continue to expose your model to these new samples with the similar features, the same features, and then adjust the weight so it's optimized for your entire training data set. And then expose that to your test data set that's never seen before. Your model's never seen the data set before for the test data to be able to make an accurate prediction. Bottom line, a neural net with a single hidden layer can approximate any function. So a neural net you can think of as a universal function. And then also there's a real benefit is that you can parallelize this. It's parallelizable in a computer architecture. So that's a real benefit for the concept of a neural net, is that it fits our compute architectures. So this universal function, a neural net with a single hidden layer and an activation function, I probably should include, allows you to really approximate any function. Okay. And so this idea of really how do you create a generalizable, your network is generalized to work on any data is the goal. And what happens, the risk is in machine learning is that you have a small data set and you fit that data set perfectly. And so here is a polynomial of 9-degree polynomial, and you can fit each data point exactly. Well, really this is a sine wave data, right? It's just that we have noise in the system. And so there is the risk with neural nets is that you really overfit the data. And so if I introduce a new data point here, we may have more error if we use in the final test data, our prediction data, is if we have an oversubscribed or overfit set of data. So what we're striving for is to fit the data properly so that it's generalizable for another set of data. So we'll spend a lot of time talking about overfitting, and then the method to reduce that, and the general term is regularization. There's L1 and L2 and dropout regularization, and we'll have some video lectures on that topic as well. Okay, let's introduce some other important concepts and kind of extend the idea of training and test data sets to include the idea of a validation data set. So you may divide your data into actually 3 different groups. And so you use, let's say 70% of your data for training, and then you compare the error to a test set. And I hesitate to call it a test set because that's your 3rd group. We're going to call it a validation set. And then you iterate on, your model iterates and reduces the error or loss and then updates the weights for this set of training and validation data. And then you try it on a never before seen set of data called a test set. Well, there's a couple of important concepts to cover here. In this training mode, you call your data or your model that's highly biased if the model is underfit, and that means that the error is both large for both the training and the validation error are large. And then as the error reduces with more complexity, you could run into a situation where your error for your training data set becomes very low, but then your validation error is very high. And this is said to have high variance. Your model has high variance. So we'll use different methodologies for dividing the data set up into different groups to be able to test the robustness and generalizability of the model itself. And that's the goal, is to make a model that's generalizable. It just doesn't work for one set of data that we can add a new set of data and test it. Okay, I think for me, when I was first learning about neural nets, convolutional neural networks really gave me an intuitive feel for how neural networks work, and we'll spend a lecture or two on this as well. So with the convolutional neural networks, they're used on image data, and you can think of these kernels, there's really filters of 0 and 1, a pixel has 0, 1 value, and the pixel is a subset of the image. It can be a 5 by 5 subset of the image with a different filter, meaning a different set of 0 and 1 values, and then that filter is passed over the image, convoluted over the image, and then, for example, if we're looking at the ear, the shape of the ear, we may be looking at that very tip, and so the filter kernel, a specific filter kernel, will recognize that tip of the cat's ear, and that'll be cascaded into the neural network in the hidden layers. So now you've recognized really what is the level of triangles, or the tip of a triangle within the image. If you have more of that, then you're more likely to have a cat than a dog, for example. So really the concept of a convolutional neural network and using kernels to find patterns or features in the image, it's intuitive to me how the neural network is learning the specific features. The other thing is these kernels can be in any orientation, and the result is the model is spatially invariant. So you can have a cat head at a different orientation and be able to find the features of the cat in the image at any orientation. So that's the power of convolutional neural networks as applied to image data, and we'll do some applications in the image application area. Another important concept is transfer learning. I touched on this already, and the idea here is that you have a pre-trained model, and I want to cut it, and I want to add my own model on top of the existing model, where I want to change the parameters, the number of neurons, the number of hidden layers, and so forth, to be able to get an improved model. And so this is called transfer learning. This is important because there are a lot of models that are public domain now that you can take and then modify. So I expect that you may use transfer learning in your final project too, for example. Okay, and then later in the semester, I hope we have time to introduce this concept of general adversarial networks, or GANs. And this is an interesting idea of how you can use a limited set of data. You kind of augment your existing system by having a system that generates or takes data and really simulates having a feature or a sample, or a set of features for a sample. It's called our X-fake. And then these models are working against each other to really improve the overall accuracy of a discriminator detection model. And so there are examples of these type of systems being used for the MNIST data set, for facial recognition, that improve accuracy and make the model much more generalizable. And so that is the idea of general adversarial networks, is really to kind of augment the data that you have by creating really fake data, fake samples that simulate new data input. So we talked a little bit earlier about how humans learn with a very few sets of samples. This kind of mimics the way that you can use a few samples to be able to create a model. All right, so that's a really quick introduction to the concepts, early concepts. I'm trying to get us through this layer here on Bloom's taxonomy, where we understand the basic concepts, we can apply them. So the early examples I'm going to give you are really taking existing models and modifying them, or modifying the data so that you can make a prediction. And then we'll introduce project 1, which we'll all work on as individually, and then you can work on individually on your own project, or a team of up to 3 people working on a piece of original work where you create your own data set and own model for a machine learning or deep learning application. All right, until next time.